In the beginning was not the Word, but there were huge clouds of dust and gas, mainly hydrogen. But the big boy gravity starts pulling them together. The dust and gas clouds become denser and attain more mass. Gravitational force between the material as a result of its weight overcome the outward pressures due to the kinetic energy of the particles in the gases, meaning the cloud collapses into small bodies because of its gravity. Material at the center heats up as gravitational potential energy is converted to thermal or kinetic energy. This hot core is known as a protostar. This protostar accumulates more gas and dust and thus increases in density and temperature. The thermal energy generated means this cloud heats up as well as the internal pressure increasing. Because the pressures can start to resist the gravitational collapse of the cloud, it stops shrinking. So the kinetic energy leads to immense heat being generated, and the protostar begins to glow, known as a pre-main sequence star. If the mass of the protostar exceeds about 8% of the Sun's mass, enough GPE has been converted into kinetic energy for nuclear fusion. This means hydrogen is converted to helium in its core. But what do we call this new stage? This is known as the main sequence star. It is typically the longest stage of a star's life, and all the glorious energy it emits comes from the nuclear conversion of hydrogen into helium. The time it spends at this stage depends upon its mass. For example, our Sun, a yellow dwarf, will spend about 10 billion years at this phase. Massive stars burn far more brightly and use up their fuel way faster to spend less time. Equilibrium is achieved between the contracting gravitational force and the internal pressures. All the hydrogen in the core that is meant to go for nuclear fusion gradually becomes exhausted. It is all transformed into helium, a noble gas. But then, all nuclear fusion in the core stops. Gravity compresses the core into a smaller size, but there is still a layer of hydrogen surrounding the core. The gravitational contraction of the core supplies enough energy for nuclear fusion of the hydrogen in this layer. This nuclear fusion leads to an immense outward pressure being exerted, which stops the star from collapsing and instead becomes hundreds of times larger. The expansion means that the energy from nuclear fusion in the hydrogen layer is spread across a larger surface area, so the average kinetic energy of the other material decreases, i.e. the temperature decreases, making the star's light output shift to a red wavelength. It is now a red giant. This happens to stars about a fifth to 10 times the Sun's mass. As a red giant, it fuses helium to carbon and oxygen, which builds up at the center. If a red giant does not have enough of a temperature, normally about 1 billion Kelvin, carbon and oxygen will remain there. The star then sheds its outer layer to form a planetary nebula, leaving behind its core. The material that surrounds the core forms a planetary nebula. To the left is the Cat's Eye Nebula. It was found in the constellation Draco in the northern hemisphere. The Cat's Eye Nebula was one of the first planetary nebulae to be discovered, and also is one of the most complex planetary nebulae known. But what about the core? A white dwarf is formed from the remaining core, composed of carbon and oxygen. Material in this no longer goes through nuclear fusion, so there's no source of energy. This makes it collapse and become extremely dense. It is very hot nonetheless, but because it has no source of energy, it gradually cools down. If it cools down enough, it will no longer emit much heat or light, so it becomes a cold black dwarf. It is estimated that this takes about 13.8 billion years, longer than the current age of the universe. So, no black dwarfs exist yet. But wait, what about stars greater than 10 times the Sun's mass? Stars above 10 times the mass of the star are massive enough to continue nuclear fusion beyond helium in its core. Carbon and oxygen form into magnesium, neon, and more. This fusion causes pressure, called radiation pressure, causing the star to expand even more. These are called red supergiants and appear extremely bright. Why don't we focus on the core? Energy continues to be released by fusion until the star's core is made of iron nuclei, which is 26 protons and 26 neutrons. When iron fuses, they consume energy rather than releasing it, so fusion ceases and the core suddenly collapses due to gravity. Now, let's put the matter back. As the core collapses, matter falls onto it at about a fifth of the speed of light and bounces off. A shock wave is produced as a result of the core collapse. The star will be brighter than the whole galaxy for about a month. A neutron star is formed if the object is about 40% larger than the Sun and are about 12.5 miles long in diameter. Black holes can be formed if the object is even more massive. And that's the life cycle of stars. Gases forming together, undergoing nuclear fusion, heating up to extraordinary temperatures, but gradually burning out and become something you can't even see, a black hole. Let's imagine you gaze at it, looking at it, and seeing a circle of total darkness. You see the stars of the sky around it, but they seem to be going towards nothing. Then you realize you're falling into the hole, moving faster and faster, your feet miles below your head, and your body remains intact if it's a supermassive black hole. If it was a small one, you wouldn't be so lucky. You keep falling past the event horizon, when you become squashed into a single point of infinite density, completely gone to the world, but still there. Kind of puts GCSEs in perspective, doesn't it?